Welcome to section 5.3. We will be discussing conditional probability.
Conditional probability lets us update beliefs based on new information. For instance, what's the chance of disease if someone has a certain risk factor? Or the likelihood of injury based on behavior? These types of questions are everywhere in clinical and public health work. We define conditional probability as the probability of event B occurring, given that event A has occurred. The formula is the probability of B given A equals probability of A and B divided by probability given, assuming probability of A is greater than 0. Visually, you can think of this as shrinking our sample space to just the cases where A happens, then asking how often B occurs within that subset. Let's say we have 100 patients. Of those, 20 are smokers. Among the smokers, 5 develop a condition. That gives us a conditional probability of 5 divided by 20, or 25%. Among the non-smokers, only 4 develop the condition. That's 4 out of 80, or 5%. Clearly, the condition is more likely among smokers. Rearranging our definition gives us the multiplication rule. Probability of A and B equals probability of A times the probability B given A. This form helps when you want to compute the joint probability from the marginal and conditional probabilities. Events A and B are independent if knowing that A occurred doesn't change the probability of B. Mathematically, that means probability of B given A equals probability of B. And if that holds, we can say probability of A and B equals probability of A times probability of B. This concept will come up a lot in modeling and assumptions. A classic example of independence is coin tosses. The result of the first toss doesn't influence the second. Similarly, in clinical studies, we often assume that one patient's recovery is independent of another's, unless otherwise stated. It's crucial to distinguish disjoint events from independent events. Disjoint events cannot happen together. So, if A happens, B definitely did not, meaning they aren't independent. Independence means one event doesn't affect the other's likelihood, not that they exclude each other. Two-way tables help us organize data across 2 categorical variables. Each cell in the table represents the joint occurrence of 2 events, and the row and column totals represent marginal probabilities. From this, we can calculate conditional probabilities. Suppose 400 patients are surveyed. 322 stretched before exercising, and 78 did not. Of those who stretched, 52 got injured. Of those who didn't stretch, 21 got injured. This data forms the basis of our two-way table and allows us to calculate various conditional probabilities. From our two-way table P, injury no stretch is 21 divided by 78, which is about 26.9%. Probability of injury given stretched is 52 divided by 322, or roughly 16.2%. The fact that these values differ tells us that stretching and injury are not independent in this dataset. In Excel, we can calculate conditional probabilities by dividing a cell with the joint count by the marginal total for the condition. Pivot tables make this even easier by letting us display values as percentages of row or column totals. In R, conditional probabilities are straightforward using subsetting or table functions. For example, we can sum over categories or use the prop.table function with a margin to get conditional probabilities across rows or columns. Bayes' rule allows us to reverse conditional probabilities. If we know probability of B given A and the overall probabilities of A and B, we can compute probability of A given B. This is especially important when direct measurement of probability of A given B is difficult, like in diagnostic testing. To apply Bayes' rule, we need to know the overall probability of event B. But what if we don't have it directly? That's where the law of total probability comes in. This formula breaks B into 2 parts. One where A happens and one where A does not happen, not A. We calculate the chance of B in each scenario and then add them up, weighted by how likely each scenario is. Formula is shown here. Means the probability of B overall equals probability of B when A happens times chance A happens, plus probability of B when A doesn't happen, times chance A doesn't happen. This approach is especially useful when B can occur through multiple paths. It gives us the complete picture of B's likelihood by summing over all possible causes or conditions. Suppose 1% of a population has a disease. The test has 90% sensitivity and 90% specificity. When a randomly selected person tests positive, we want to know the probability they actually have the disease. Bayes' rule shows that despite a positive result, the chance of truly having the disease is only about 8.3%. A tree diagram breaks the problem down visually. The first branches show disease status. The second, test results. Multiply along path to get joint probabilities. This diagram reveals that most positive tests are false positives due to disease rarity. In Excel, calculate Bayes' rule by entering the components in different cells, then dividing the numerator, the probability of B given A, multiplied by the probability of A by the denominator probability of B. This setup helps clarify and verify each part of the computation. In R, we define each probability, calculate the denominator using the law of total probability, then plug into the Bayes formula. This is fast and avoids manual rounding errors, making RStudio great for scaling up to complex datasets. To wrap up, conditional probability refines our understanding based on new info. Independence, when valid, simplifies analysis. Two-way tables help extract these probabilities, and Bayes' rule lets us invert them. Tools like Excel and RStudio make these computations accessible and repeatable. Mastery of these ideas is essential for evidence-based reasoning in biostatistics.